Hello everyone, myself Ashish Desai, Assistant Professor, Mechanical Department. Today we are going to discuss here the unit number 5, types of flow. So in that content we are going to discuss the power absorbing bearings and Reynolds experiment. So first of all we look at the power absorbing bearings. So as you know that the in a bearing a very thin film of lubricating oil is maintained between the stationary surface and the surface of rotating shaft for reduction in the friction. So the lubricating oils are viscous, therefore we have to apply the theory of lubrications. So as you know that a very viscous oil leads to greater resistance and causes a great power loss. But in case of light oil, it can be may not maintain a required film between the metal surface and wear of the surface will take place. So this type of expressions for power loss we will discuss in a different way. So in that different types of bearing is there. So first of all we discuss the journal bearing, then we will discuss regarding the footstep, and third we will discuss regarding the collar bearing. Now we are going to discuss here the journal bearing. So here the shaft is mounted between the sleeve, and in between that the oil film is there. So whenever the rotating shaft is there, so therefore friction will be less because of this oil film. So this figure shows a journal bearing, which is the shaft is rotating and the sleeve is stationary. So in that content capital D, so this is the capital D. So this is the diameter of shaft, thickness, that is T. So here already mentioned this blue, that portion is called as thickness of oil film, and the length, so the shaft length is L, so we consider the length of bearing, that is L, and N is the speed of the shaft in RPM. So this is the given data. Now we will discuss regarding the angular speed. So whenever it rotate about the sleeve, so that will gives the angular speed. It is equal to 2 pi n divided by 60. So this is in terms of radian per second. So this is the V. As you know that the tangential speed of the shaft, for tangential shift we can say that V is equal to omega r, right? So omega is nothing but this angular speed, so we can write 2 pi n by 60. So this is the omega, and this r is nothing but d by 2. So we have to considering the radius here, but we consider here diameter, so we can write d by 2. So after that with solution we will get the pi dn by 60. So whenever v is there we can write pi dn by 60. So this is regarding the tangential speed of the shaft. So this is thickness T, is a very thin, very small thin is there. Therefore, the we can consider for the various velocity distributions. So velocity distribution is nothing but du by dy, or can say velocity gradient. So du means change in velocity. So change in velocity means final velocity minus initial velocity. So final velocity is v, and initial velocity minus 0. So that's why final velocity can take v by t. So here we can write v by t, and v is nothing but this. So already we discussed v is equal to pi dm by 60. So this v, that is the tangential velocity, you can put up that directly. So that equation becomes pi dm by 60t. So as you know that shear stress, so here the shear stress is caused over here. So that's why tau is equal to mu du by dy. So this is about the oil film, so mu du by dy, right? So as you know that du by dy means pi dn by 60t. So as we can write here, right, pi dn by 60t. So as you know that the shear force, so shear force means actually shear stress into area, or can say tau is equal to force upon area. That means force is equal to shear into area. So here shear into area. So this shear we can put over here, and area of surface, so you can put here area of surface of shaft, then we get the frictional resistance, or can say that viscous resistance. So I write as it is, that is force is equal to tau into area, that is nothing but area of surface of the shaft. So area of surface of the shaft means pi dl, because this oil is along the length. That's why we are considering the peripheral area, that is pi dl, or can say circumference area, pi dl. And this tau we already calculated in that before this session. So that yes, this is the tau is equal to pi dn by 60t. So this is the equation we can directly put over here, that tau, this is previous value, and area of surface, so area of surface is that we can say pi dl, because about overall the length. So because of this overall length, it will be causes that stress test. Okay, so that's pi dl After cancellations and that solution, we get the pi f is equal to pi mu pi square d square in L divided by 60t. Then we'll next go to the power absorbed in the that overcome the resistance. P is equal to T into, or can say torque into omega. So this P omega is, we know that W pi n, sorry, 2 pi n by 60 and T as it is. So power, whenever you get for power, P is equal to 2 pi n by 60. This is in terms of watt. So this is about the real solution for journal bearing. So whenever we have to find out for power absorbed in the overcome resistance, so you can go for this P is equal to 2 pi n by 60. If you know the T, that is torque, and speed, then we directly we get the power in terms of watt. So this is about the journal bearing. Now we move for the problem on based on this. So here the clearly mentioned that a shaft of 100 mm diameter. So this is 100 mm diameter. D is there given to you, that is rotates at 60 rpm. So this is n in a 200 mm long. So this is a length. So this is diameter. This is n, capital N, that is rpm. That's why speed is there. And 200 mm long, that is meant L, capital L. Taking that, the two surfaces are uniformly separated by a distance 0.5 mm. So this is thickness, oil film thickness is there. So this is separated distance between two surfaces. And taking linear velocity distribution in the lubricating oil having the viscosity, dynamic viscosity there 0.04 pi. So mu is given to you, and find the power absorbed in the bearings. So here the length of shaft is there, that's why we can imagine that this is journal bearing. So first of all, we go for the solution basis and given data. So their diameter D is 100 mm. So already we discussed. So that is why 0.1 meter. Then shaft, that is speed is given to, that is n is equal to 60 rpm. The length is 200 mm. So convert into this meter. So here also convert into meter. Then thickness of the film, that is T. So the separate distance is 0.5. So convert into this meter, 0.5 into 10 to minus divided by 2. Then next, dynamic viscosity mu is equal to 0.0 points, 4 points. So if you divide by 10, then you get the 0.004 Newton second per meter square. So this is about given data. And now we find out here power required, right? So sorry, power absorbed. So here we know that the torque we have to calculate for general bearing is like this, because already we discussed this formula. So this is torque, because P for calculation of power, P is equal to 2 pi n by 60. So 2 pi n is known to you, 2 pi is constant, T is unknown. So here we can write T, because 2 pi n T divided by 60. So 2 pi n by 60 is known to you, it is constant, and torque is unknown. So for finding out the torque for general bearing, we write the relation and then we put up the value. So that mu is 0.004 pi square as it is, capital D is 0.1 cube, n is 60, L is 120 as it is, into the T is thickness of the film, that is zero point 0.5. So but convert into meters, so that's why 0.0005. So after that solution we will get the torque 0.0700789 Newton meter. Now we know that the power absorbed is equal to 2 pi T by 60, and here 2 pi as it is, n is 60, T is, so T is already we calculated over here, that is 0.00789. We take this as it is divided by 60. So again I repeat this 2 pi as constant, n is 60 rpm is given to you. Then torque is already mentioned here, 0.00789. So we calculate here, and after that we find out the power absorbed. So this much amount is power absorbed by the bearing. So this is regarding the journal bearing. Now we move for the footstep bearing. So in footstep bearing, so actually the footstep bearing is at the end of vertical shaft, and the space between the surface of the shaft and bearing is filled with oil, the viscosity mu. Now we move for the given data, that is r is the radius of shaft, then n is the speed of the shaft, and t is the thickness of the film. So here I'll clearly mention that the blue lines indicating the thickness of the film, and here the sleeve is there and the shaft is rotated. So this is about the footstep bearing. So already mentioned this circular ring is there. So that is radius of r, and thickness, that is dr. Thickness is dr. We are assuming here that is thickness. Okay. Now we move for the area. So actually we already discussed here, that is area of elementary ring. So whenever elementary ring is there, 2 pi r into dr. So because of we are considering the circumference, we consider as area for the ring is 2 pi r into dr. Now we know that the shear stress is equal to tau is equal to mu du by dy. Now du by dy, so instead of du we can write as a v, and dy, the dy is the thickness of the film, that is why we can write t. So already we know that the tau is nothing but mu du by dy. So this relation is called as Newtonian fluid, or you can say Newtonian law of viscosity. So that's why shear stress is equal to mu du by dy. So now mu and tau is same as it is. Du means change in velocity, that's why I can write v, because initial, when final velocity minus initial velocity, final velocity is v, initial velocity is 0. So that's why v is the tangential velocity. Now we take as it is two terms, that is area of elementary ring and shear stress. Area of elementary ring and shear stress, that is tau mu du by dy. Instead of that we can write v upon l. So v is the tangential velocity. V, that v indicates the r omega, or you can say omega r. The shear force, so shear force is nothing but, already discussed this, the shear force is equal to tau into area of ring. So tau we can put mu v upon t into area of ring, that is 2 pi r dr, that is about shear force. Now we put the value for v, because v is unknown, known to that is tangential force, that is 2 pi n by 60, and this terms we can directly we can put up here, and the area for the ring is 2 pi r dr. So this is the term for the shear force. So after simplification we will get the mu by 15 into pi square n r square by t into dr. Now torque on the rings, that is why we can take force into radius, because torque is nothing but force into radius. The smallest force is there, that's why I can take as a df into the r. R is the small. So this is the relation. Now put up the value over here, that is mu by 15t pi square n r square dr. So this is about shear force into r. So this is r means elemental area. So after calculating these two terms, here we get the value for, this is torque of the ring, we can take as it is and collective over here. Now we can take the overcome resistance 0 to r. Okay, so this is the torque required to overcome of this resistance. So we put the value over here directly. So q 50t pi r square into capital N 0 to r cube dr. So instead of r cube you can write integration of this r is to 4 divided by 4. So 0 r. So you can put the 0 r over here, and this is the final solution for the collar bearing. Now power absorbed by the entire bearing, that is P is equal to omega T. So T is, we know that is torque, and omega is nothing but 2 pi into 60. So this term is in the inverse of watt. So based on that we will take the example to find the power required to rotate a vertical shaft of a diameter 100 mm and at 750 rpm. So this is the parameter, and which is vertically included shaft is there which can rotate over here. So that is nothing but the collar bearing. So as term that the footstep bearing is there. So this footstep bearings is having, we can say that diameter of shaft D, capital D is 100 mm. So we convert this 0.1 meter, and capital 7, that is 750 rpm. T is 0.5 mm, 0.005 in terms of meter. Mu is the value for viscosity of oil. So that should be 0.5 poise here already given to you. That is why we convert this divided by 10 for Newton second meter square. Then power required for the foot bearing is, so this is the relation for torque, because P is equal to 2 pi into 60. So power is possible, but for torque purpose we will get the value relations. So put up the value here. Mu is nothing but this 0.15, that is viscosity of oil, 60 as it is. T is the term, that is the thickness of oil film, that is 0.0005 pi square as it is, capital N is 7050, and small capital R is 0.1 divided by 2 bracket raised to 4. So this is term for power required. Before that we calculate this torque. Now we go for power required. So that is P is equal to 2.2 by 60. Then put up the value over here, and then we will get the value for the power, that is in terms of watt. So this value will give the relations as well as the finding out the that power required to rotate the shaft. Now we move for the collar bearing. So collar bearing, which takes place the axial thrust of the shaft, and the face of the collar is separated from the surface. So collar and the surface, that the face of collar is separated from the surface of bearing with a film of uniform thickness, which is maintained by a forced lubrication system. So this is forced lubrication system. When one of the example is there. So therefore, so capital R1 is there and capital R2 is there. So this is the bearing surface, and here the arrow indicates the bearing surface. R1 is the internal radius of the collar, and external, that is R2, for the external radius of the collar. Then thickness T is for oil film, and capital N is the speed of the shaft. And then considering this elementary ring is there, and for that purpose we already calculate the for area of elementary is 2 pi r dr. And then next, that is the Newtonian fluid law, that is tau is equal to mu du by dy. Instead of du we can write v upon t, that is t for the thickness, because du by dy is the thickness of the film, du is the velocity. So velocity we can keep as it is, that is v, and t, that is small t. Okay, so this is for thickness of the oil film. So as we know that v is nothing but r omega, so we can know that the shear force is equal to tau into area of the ring. So you can put the a tau value mu v upon t into area of the ring, that is 2 pi r dr. So after solution, that is v is nothing but r omega. So before that we can put the omega value, that is 2 pi n by 60. So after that calculation, that df is nothing but this mu 15 pi r square n r square divided by t. So this is about the shear force. Now we know that the shear force into the radius. So you can put the finding out the torque over here. So torque is as it is, that df is can take as it is into r. Now this relation we used to for finding out the torque, because already we discussed this all the terms that is related with the torque on the ring. Now this total required to overcome the friction, that formula is same, that is P is equal to, that is the torque. Here we can calculate for total, because this is elementary torque we can calculate. So after that, for evaluation from R1 to R2, we will get the value for the R, that is R raised to 4, because R cube is there now, only this term is all constant, that is mu by 15 miles square n bracket, that is the constant one. But r1 r2, that is small r cube dr, so we can calculate here r is to 4 by 4 r1 by r2. So according to that we can manage it, that is torque. And then power required for that, p is equal to omega t, that is why we can take as a 2 pi n t divided by 60, that is the power absorbed, which is in a rp, that is which is in a watt. Now we will take the example for the collar bearing. So as you know that the collar bearing, the external and internal diameters of 240 mm and 180 mm respectively is used to take the thrust of shaft. An oil film of thickness is 0.25 and of viscosity is 0.8 poise and is maintained between the collar surface and the bearing. Find the power lost in overcoming the viscous resistance of oil when the shaft is running at 300 rpm. Now we take the given data first. External diameter is there, that is 240 mm. So we convert for the external radius. So that's why R2 is equal to 240 by 2. That becomes 120 mm. And after this conversion is 0.12 meter. Now next that radius, that is internal radius. So R1 divided by 180 divided by 2. So this is about 90 mm. So convert this into 4 meter. Then thickness of oil film is 0.25. Then mu is zero point 0.8, so that is zero point 0.8 poise. So convert is this for divided by 10, that is for Newton second per meter square. So whenever 0 0.8 there, so we can divide by 10, so directly we get 0.08 Newton second per meter square. Then shaft of the speed, so that is about 300 rpm. Now we go for the power lost. So power lost for that, because V is equal to 2 pi nt by 60. T is unknown to you. That's why we calculate for T first. That is T is equal to mu 60 T pi square. Sorry, pi square into N R2 raised to 4 minus R1 raised to 4. So we put the value over here. Mu we can take 0.08, 60 as it is. T is 0.25. So we convert this meter 0.00025. Then R raised to 4. So R2 raised to 4 is there. So 0.12 raised to 4 minus 0.09 raised to 4. So after that we calculate the torque over here. That is power that lost in viscous resistance. Then we know that relation, that is P is equal to 2 pi by 60. So put the value of 2 pi as it is. N is, we can take it directly. Then T is the torque. So already calculated, that is 2.238 and divided by 60. So after that calculation we will get the value per power, that is 70.31 watt. Now we move for the next terminology, that is the Reynolds experiment. Before that we will observe this terminology. For example, journal bearing. So if you go for journal bearing, so you will get the, sorry, so this is about the valuation for journal bearing. So here we have placed the rotating shaft into the sleeve, and in between that oil film is formed like this, and this will gives the relation for the power required, or can you say power absorbed in the bearing. Now we move for the next terminology, that is, this is the collar bearing. So already we discussed this point. Then T, that is T for that, mu is 0.08, then 60 into 0.00025 pi square. N is 300. R2 is the 0.12 minus R1 is 0.09 raised to 4. So after simplification we get the torque over here. Then P is equal to 2 pi nt by 60. So we put the value over here and then find out the value of watt in terms of 70.31 watt. So watt we can take as it is. Now we move for the Reynolds experiment. So this first diagram indicates that Reynolds apparatus. So this is a supply tank. Here the wall is there. So whenever the dye, so dye content is the dye means when potassium permanganate is there. So we can take the with water, then this color will form. So after we can dropping from this point to this point. So whenever get the straight line, so we can identify that is the laminar flow. So if it is go like this, that is called as wavy filament, and if it is go for in a distributed manner, that is called as a diffuser filament. So this type of observation we will made on basis of Reynolds experiment. So this is a color we have dropped from here, okay, and then we observe the flow pattern. So this is requirement. Following requirement is there: a tank consisting with water at constant heat, a small tank containing the some dye. Then third one, the glass tube having a bell mouth entrance at the one end and regulating the wall at other ends. So this is about the Reynolds experiment. So already we mentioned that there are three types of flow is there. One is a laminar flow, second is a transition, third one is a turbulent flow. So in we know that the laminar flow is nothing but difilament, then wavy filament, and this third one is the that is called as turbulent flow is there. So that is called as diffuser filament. So in that content, as we know that the laminar flow is there, so loss of head was found to proportional to velocity. So both are the proportional manner. So this is the loss of head. Then next for turbulent flow, the Reynolds observed that the loss of head is approximately proportional to the square of velocity. So mostly the loss of head, that is HF, is proportional to Vs to N, where N varies from 1.75 to 2. So this is regarding the Reynolds experiment. So we can easily identify by observations or by practicals. So this is about the Reynolds apparatus, or you can say Reynolds experiment. So here clearly mentioned there is a straight line, that is laminar flow. This is the zigzag in the transition. Then distribute. First of all, it should be a wavy, but after that it can be diffused. So this is called as the different stage of filament. So in this session we already discussed this point regarding the power absorbed in bearings. So first of all we discussed the general bearing, then collar bearing, uh, then footstep bearing. After that we discussed regarding the Reynolds experiment.